So now we have learned about very basics like probability, events, conditional probabilities, etc. So now we are slightly getting more, going into deeper, in the sense you are talking about an event, right, which has multiple outcomes, right. You are talking about an event which has multiple outcomes. I want to characterize that. So you are talking about an experiment which has multiple outcomes. I want to characterize that experiment. What am I wanting to do? I want to characterize the experiment itself. What do I mean by that? You are doing an experiment, I want to characterize that experiment, a random experiment. How do I characterize it? You understand my question? You are tossing a coin. I want to characterize this experiment. What will you do? What does it take to characterize a tossing of a coin experiment? You understand my question? Till now we talked about probability, what is an event, etc. Now we are interested in what? Not just one number, we are interested in outcomes of the experiment, right, and then derive quantities that will describe this experiment itself, so that I can develop stats to describe this experiment, okay, using sample. Now how do I characterize an experiment? What is the best way to characterize an experiment? Let us say tossing of a coin. What do? The experiment is, I will start from simple and then take it complex. Tossing of a coin. What is the sample space? Head and tail. Now how do I want to characterize this experiment using numbers. How do I do it? Probability for each outcome. Okay, probability for each outcome. Okay, then is that numbers now? Probability of head equals to 1 by 2, probability of tail equals to 1 by 2.
Both are equal, so maybe we assign 1, 1 to each or 2 to each.
Okay. So here is what I am we are going to do. When we say characterize an experiment, I want numerical outcomes. Let us be very clear. I want numerical outcomes when I talk about characterizing, right. So the first step in doing that is converting the outcomes to a real number rather than having it in a descriptive fashion, okay. So now any experiment, I am going to define a variable called a random variable or random variables. If multiple outcomes are of interest, we call it as random variable or random variables depending upon what we want. So a random variable is a variable that assumes numerical values associated with outcomes of an experiment. So the sample space is converted into a real line. So this is what I meant by, so if I say my range of the numerical experiment is, this is my domain, I mean this is my sample space, right. The sample space could be numeric, could be not numeric. The head in tossing of a coin, it is not numeric. The sample space is head or a tail, it is not numeric, right. Now what do? The simple example, sample space, I have two outcomes. I use a random variable called x that maps head to 1 and tail to 0. So x assumes 1 when head and tail when, and 0 when tail. What have I essentially done? I have converted the sample space, or I have mapped the sample space into a real line. That is the first step. Why? Because if I have to quantify or characterize, then I have to convert the sample space into numerics. I cannot have good, bad, ugly and then talk anything numerical. I have to map the sample space to a real number. That mapping is done by using a variable called random variable. Now I can ask a question, what is probability of x? What is P of x? Now the entire experiment is characterized by a variable called random variable. You don't talk about sample space, etc. You simply say x is the random variable that describes the temperature in this room, period. X is a numeric, in this case x is a numerical value which takes any number 0 to infinity, right. So now on, when you talk about random experiment, the moment we think of random experiment, you have to think about a random variable associated with the experiment which maps the sample space onto a real line, okay. Now the next question I can ask is, what is the probability of x? Probability of x, is it going to be one number now? Earlier it is one number if you are, because you specified one outcome. Now probability of x is what is going to be it? It is going to be a, it's going to be a distribution. Why? For a head it is 1 by 2, for tail it is 1 by 2. Now what is x? For 0 the probability is 1 by 2, for tail, for 1 it is probability is 1 by 2. So does it have one number? It is a distribution. So if I have to talk about probability of x, I will have what? 1 by 2 for 0 and 1 by 2 for 1. So it is the distribution of, probability distribution of x. It is not probability of x, it is distribution of x, because x is supposed to take multiple values, and for each value of x you have a probability, and when you plot P of x, it is a probability distribution. That is why we call it as probability distribution, okay. That is why the title I have mentioned it as probability distribution. So what characterizes the random experiment now? Probability distribution of random variable, not just the random variable. Random variable is nothing but the sample space. If I want to know the maximum about random experiment, what do I want to know? I want to know the maximum possible about a random experiment. What is the maximum you can know about a random experiment? The probabilities of the outcomes. Anyway you know that you cannot know the exact outcome. By definition you cannot know the exact outcome. So what is the maximum you can know about the know about this? What is the maximum you can know about the random experiment is? Probabilities of the sample space, in which case it is nothing but probabilities of the random variable x. So P of x is the maximum one can know about the random experiment. Clear? Does it make sense? P of x is the maximum one can know about the random experiment. Understood? But can you get P of x from your sample? So the maximum you can know about is what? P of x. True P of x will you ever know? True P of x you will never know. It is like, if you know, it is next to what God knows, to be frank, because that is like knowing the truth. True P of x is not known. True P of x, if you know, that is like the maximum one can, mankind can know about a random experiment, maximum is true P of x. Unfortunately true P of x is also not only truth is not known, true P of x is also not known. Philosophically people say, right, truth is not never known. Truth is never known, because by definition of a random experiment you say that the outcome is uncertain. Not only that, true distribution itself will not be known. Why? If you want to estimate true distribution, what is probability by definition? What is probability by definition? Frequentist approach. What is probability by definition? Limit n tends to a, n tends to infinity, n of a by n. So if you want to know to measure the true probability distribution, what you should do? Or if you want to measure the probability of x, measure it with a very high accuracy, what do you need to know? N has to be infinity. Can you do that? That is like measuring the entire population, not possible. So true P of x is never known, and it is also very bad idea to estimate P of x. Okay, I will tell you even before I jump further, P of x is never known to you except for simple cases, except for throwing of a coin, tossing of a coin, which are all not that much interest to us. There P of x will be known to you because that is a simple experiment, but in all real life situations P of x will be never known. What is the probability distribution of my voice at various frequencies? Everybody is biomedical engineers, most of you know what is frequency. Why is it important? Probability distribution of my frequency of my voice, why is it important? Voice recognition. You say Google, it recognizes you, how does it do? What does it look for? Distribution of frequency content of your voice. That is what is unique to you. Your vocal cord, the way you generate is different from me and different but unique. What to look for? Fingerprint, iris, all of this is what? We are looking at the distribution. And to give you an idea, 10 years back, your voice recognition in Siri or mobile apps would be pathetic. Today, how is it? It recognizes your voice also. Earlier it is mainly Caucasian. Today it is possible for every country. Why is it? That is one area where speech recognition, where people have tried estimating the probability distribution itself because of availability of large amount of data. Google recorded billions of voice data. Okay, so they also call it as an experiment. Speaking is an experiment for them. You may wonder what is there, but they will have big recorders, data storage. It will be hundreds of millions of people voices processed, so that they can train their networks to be accurate. Today, even if you speak, or even in a remote village, somebody speaks even in Tamil or native language, Google still picks it up. Why? They are trying to estimate the probability distribution itself, which is next to the maximum one can know. Okay, but that would require huge amount of investment and data. So typically we do not estimate P of x. Although P of x is the maximum one can know about a random experiment, P of x is not estimated from the sample. Why? Because it is very costly. There are very few applications like signal processing, speech processing, where people have tried estimating P of x. Today Alexa is very common, anybody's voice it will recognize. That is because there is so much amount of data which is used. Okay, so P of x is the ideal thing to have, but estimating P of x is very difficult, keep in mind. Okay, and P of x will itself depend upon two kinds of random variables. One is continuous, the other one is discrete. Okay, discrete, the sample size is limited. Continuous, the sample size is larger. I told you with decimal points. Discrete is typically like integers, the sample space is restricted, whereas the continuous random variables, the sample space is typically larger, and depending upon that your probability definitions will also vary. For a continuous random variable, as I told you, I cannot ask what is the probability of a single point. Why? Probability is defined usually over what? Over an interval within this region, an area, right? Whereas for a discrete random variable, you can talk about point probabilities. Okay. And now a probability distribution is also the same rules of probability, because it is a collection of outcomes. Probability distribution, random variable is nothing but assigning numerics to the sample space, that is all. So probability of random variable is nothing but assigning probabilities to all the outcomes, that is what it is, and all the rules of probability follow. And if you want to look at this is the plot, usually happens this way. So this is like probability distribution of x, two graphs I have shown you, right, x in the left and the right. Okay, you can think what is now the probability doing here? what is the probability here? It is like weighting for each number, right? Your outcome 0 is weighed high here compared to outcome 1, 2 and 3 and 4, right? So probability is like a weight associated to the outcome. You understand? Probability is nothing but weight associated to the outcome of an experiment. The more the probability, you know that the more likely it is going to happen. It is more. So now look at this, these two distributions are different on the left and right. Now I want to characterize this probability distribution. How do I do it? I want to characterize these two probability distributions. Remember, I cannot estimate the probability distribution from sample. We have to always keep in relation with statistics. That is what will be missing in books. What is important is I want to characterize this probability distribution using statistics, using data. One thing I told you is what? You cannot characterize this probability distribution completely because it will require large amount of data. So we will not estimate the probability distribution. But still I want to be able to distinguish between these two probability distributions. How can I distinguish? What is something different about these two distributions? Anybody tell me, Kevin, what is different about these two distributions? Look at the left and right. How do you characterize? How do you distinguish between these two? Okay. So will both the center points be same? No. Is there more to the left or more to the right? More probability in the first case, there are more probability to the left, whereas in the other case it is like morely uniform, right? And there is a peak in the first one to the left. Again, here how is the peak distributed? Almost equal. Now related with your mean, variance, etc. That is what we are doing actually. When you talk about mean, variance, etc., what are we trying to do? We are trying to characterize the probability distribution of the random variable. Mean is a way to characterize a probability distribution. Variance is a way to characterize probability distribution. Skewness, left or right, is a way to characterize distribution. The kurtosis or the peak with the valley, that is a way to distinguish. And there are cumulants, etc. I will not get into, there are several orders, but these are ways to characterize the probability distribution without even knowing the probability distribution. Okay, we will do it from the samples. How to do it, we will talk about it. Okay, so now so far good, so far so good everybody, right? What is the probability distribution, why is it important, and we are characterizing, and some of the ways to characterize the probability distribution is using these quantities. Okay, and we all know what is a cumulative distribution. I do not think I should explain, it is summation of probability distributions. Okay.